partial differential equations. Okay, the first section is we will deduce basic concepts of PDEs. All right, so a partial differential equation is an equation involving one or more partial derivatives of course, an unknown function. Right, so we call it u. Right, so this function depends on two or more variables. Okay, and this variables is often term t and 1 over several variables in space. Okay, so and the order of the highest derivatives involved is called the order of the PDE. Okay, so that we know so this define the order of a PDE, okay, and by the order of the highest derivative involved in this PDE. Okay, and then a type of PDE which is very important in science and engineering. It's called a linear PDE. So a PDE is called linear if it is of the first degree in the unknown function u and its partial derivatives. Okay, otherwise it is called nonlinear. Right, so for example, a general second order linear PDE in two variables x and y, okay, is of the form. Okay. So second order, which means that the positive derivatives involved in the PDE x at most second order. So which makes that second order derivatives. And because of it's linear, so in this equation, the unknown function u and its positive derivatives up to the second order derivatives will appear of the first degree. Alright, so this is the second order positive derivative. Alright, with respect to x and x here. Alright, and the coefficient, okay, is a1 xy, a2 xy, uxy, at a3 xy, and uyx plus a4 xy, uyy. Okay, so there are four second order positive derivatives of u, right? There are four. And there are two first order positive derivatives. Okay, so ux, so this is the first order positive derivative of x. The other one is uy. Okay, and finally, the unknown function itself, and it's equal to f of xy. Okay, so this is the a general form of a second order linear PDE in two variables x and y. Okay, so the u function, the unknown function u, is a function of x and y. Okay, and as you will see, that because it's second order, right? So that u xx, u sub xy, u sub yx, u yy. Okay, so these are all positive derivatives, right? And the unknown itself. And you can see 1, 2, 3, 4, 5, 6, 7. This is 7 functions appear in this equation in the first degree. Okay? In the first degree, because each is a function of xy, right? This is a function of xy, this is a function of xy. So we have 7 functions. Okay, 4 of them are second order positive derivatives of the unknown function u. 2 of them are first order positive derivatives of the unknown function u. And one of them is just the unknown function u itself. Okay, so you can see they appeared only first order, only first degree. And the coefficients here, you can see the coefficients depends only on independent variables x and y. Okay, so where? AI, xy, and f of xy are functions of the independent variables. Okay. Okay, and then A1, x1, A1, this A1 function is called the coefficients of this several other partial derivatives, okay, etc. For example, A4 function is the coefficient function of the term for u or y, okay. A special case, if the coefficient functions AI, okay, are constants, which makes it independent of x and y, then the PDE is called linear with constant coefficient. Okay. So linear PDE with constant coefficients are very common in practice. Okay. Of course, the f of xy can be very general, just a general function of x and y. Okay, and we call a linear PDE homogeneous if f of xy is equal to 0. Okay, so if a function, let's say, if the f function is the 0 function, okay, so for here, so if this is 0, then this is become to a linear, a homogeneous linear PDE. Otherwise, it is called inhomogeneous. Okay, so let's take examples. So the following are important second order linear PDEs with constant coefficients. Okay, this linear PDE will be studied in this chapter, the one-dimensional wave equation. Okay. this is the wave equation. So here, okay. So this is the second order partial derivative, and this also second order partial derivatives. Okay. So this corresponding to that this is constant, and this is constant. Yeah. But the other terms are all 0, 0, 0, 0, 0, and 0. Okay. So this is a homogeneous linear PDE with constant coefficients. So this is called the one-dimensional wave equation. The one-dimensional heat equation right? So this is the first order partial derivative of u. And this is second order partial derivative of u here. Okay. Again, this one-dimensional equation is a homogeneous equation. The two-dimensional Laplace equation okay. So here, the unknown function is a function of two variables and y. And these two variables are spatial variables in the plane. Okay, in the plane here. And the two-dimensional Poisson equation. The two-dimensional Poisson equation okay, so that this is the first inhomogeneous linear PDE with constant coefficients. Okay, appears in this example because the previous series are homogeneous linear PDEs. Okay, and this one, the Poisson equation, is inhomogeneous. Okay, it's inhomogeneous. The two-dimensional wave equation okay, so this wave equation describing the traveling wave, okay, actually the so-called the plane wave, okay, and the one-dimensional equation describing the propagation wave along the real axis, the x-axis. Alright, so just one-dimensional wave, so that the wave are traveling, okay, as time goes on, linear traveling along a line. But here, describing a wave traveling on the plane. Okay, so that this is the plane wave. About that. And the three-dimensional Laplace equation. So equal to 0. Okay, so there are famous and important second-order linear ODEs. Okay. And second-order linear ODEs very commonly appear in physics. So, for example, in the electromagnetic theory, okay, that we used wave equation that describe the EM wave. If by some symmetry, if you model the EM wave will be a wave traveling along the real line, then it becomes to be one-dimensional wave equations. Okay, and but in case that you can describe the your wave for under certain symmetric conditions, then propagating along the plane, then it becomes to a plane wave. Okay. In general, it will be a wave along the space. Okay, so of course you can have a three-dimensional wave equation, of course. Yeah. Okay, so but in physics, it's also in other discipline, they are important nonlinear PDEs. Okay, and among them, there are some types of nonlinear PDEs that can be solved with the theory of linear PDEs. Okay, and so let us classify nonlinear PDEs. So there are three main types of nonlinear PDEs. The semi-linear PDEs and the quasi-linear PDEs, and the last one, the so-called fully nonlinear PDEs. Okay. Right. So as you can from the meaning, we will see semi-linear PDE and linear PDE is very close to linear PDEs. And the quasi-linear PDE is a little bit far away from semi, from linearity. Okay, linearity. So let's give a proper definition. Okay. Okay, so semi-linear PDEs are non-linear PDEs which are nearest to linear PDEs. Okay, where only the highest order derivatives, only the highest order partial derivatives appear as linear terms. With coefficients that are functions of the independent variable, only the independent variables only. And the lower order partial derivatives and the unknown function may appear arbitrarily So we take an example. A general second order semi-linear PDE in two variables. Okay, is of the form So now, because it's the second order, so the highest order partial derivatives appears will be uxx, okay, and uxy, uyx, uyy. All right, and the lower order partial derivatives here will be first partial derivatives can be appears arbitrarily, including the unknown function. Okay, so that ux, u sub x, u sub y, uxy, okay, so this is a function of five variables, okay, and including the two independent variables, okay. So u is not independent, right, because u depends on x, y, right? And also u sub x, u sub y depend on u because they are first order partial derivatives. But for the highest order partial derivatives, these four, the coefficients, so they appear in the first degree term, right? So each of them appear in the equation in of the first degree. And the coefficients are still functions of independent variable xy only. So you can compare this semi-linear PDE with this linear PDE. You can see that only the first 4 terms are kept. So you can see these 4 terms are kept. Okay? And the rest can be arbitrary. Yeah. So it just, okay. So only the highest order positives appear linearly. Okay, and this is quite arbitrary. Okay. So for example, the function can be function like it can be here. X example, right? So that might be really complicated. Yes? I'm sorry? XY? Oh, okay. The nearest one, so you differentiate. You take the positive derivative with x first and the y the second. Okay? Right? Because this is the nearest to y, to the unknown function. Okay, so we keep the highest order derivatives in linear terms, in linear form. So this is called the semi-linear PDEs. Okay. And the second type, in quasi-linear PDE, the highest, so the highest order partial derivatives likewise appear only as linear terms, but with coefficient, okay, possibly functions of the unknown and lower order partial derivatives. And it's lower order partial derivatives. so that the coefficients in quasi-linear PDFs may not be function of independent variables only, so that they may depend on the unknown function u as well as its first order partial derivatives. So, for example, a general second order quasi linear PDE in two variables is of the form. Okay, so A1, you may have ux, u sub y, u xy, u xx plus A2, u sub x, u sub y, u xy, u xy plus A3, u sub x sub y, u xy, uyx plus A4, u sub x, u sub y, u xy, uyy, okay, plus f of ux, uy, u xy, u0. Okay, so that okay, and actually many important or fundamental PDEs in physics are quasi-linear PDEs. For example, in general relativities, there is an important equation called the Einstein equation, and the Einstein equation is actually a quasi-linear PDE. Okay. All right. So this is the second table of the linear PDE, and a PDE without any linearity property without any linearity properties is called fully nonlinear. And actually possesses linearity. That possesses linearities on one or more of the highest order partial derivatives. Let me take an example. Alright, so an example is the Mount Ampere equation. Okay, Mount Ampere. So let me write it down. It's okay, and it's right. So this term is a quadratic term involving the highest order partial derivatives. Okay, so this is a second order, right? This is second order partial derivatives, and so there are four highest order partial derivatives, and this four involved in this nonlinear term, right? And they have so actually there are two nonlinear. So this is the second degree, right? So this is the product of two partial derivatives of the second order, and they share the same vectors, which is a function of the first order partial derivatives, the unknown function, and the two independent variables. Okay, as well as xx plus a2 okay, plus a3 a4 plus okay. Alright, so the rest terms, the rest, you can see there are terms appear in the quasi-linear PDS, right? But in addition to all these terms, there are two terms of second degrees. Okay, so this is called a fully nonlinear PDEs. Okay, so this is a huge class of PDEs, okay, called Munch-Ampere equations, and it appears in differential geometry. Okay, of course, physicists use differential geometry to study the physics in space. So, okay. So there are a lot of endeavors to find method to solve this kind of equations. Okay, and you can see this is very complicated. Yes?
Is linear, nonlinear, one of the
Nonlinear?
yeah, if it's nonlinear and it's one of
Well, because anything, okay, if it is not linear, not semi-linear, not quasi-linear, then it is called fully nonlinear. Yeah. So fully nonlinear is the rest. Okay. It's still a very big class. You know that they are very big classes, and the Munch-Ampere equation is just one of the fully nonlinear equations only. Yeah. And the study of PDE is a very huge subject. In general, it's very hard so to have a comprehensive study of the partial differential equations. If you go to a library to check out a textbook with title partial differential equation, it should be a big book. And also you say, okay, I just studied part of the subject. They are very humble. And indeed, the study of PD is still ongoing today. There are still a lot of unsolved problems. And the mathematicians put effort on this subject even nowadays. So I can see in the future still a lot of mathematicians, they would like to put more efforts to study the PDEs. Okay. So compared with the ordinary differential equation we learned last semester, the subject, the subject of ordinary differential equation is, I think, is much smaller. Okay, and I think by the end of the 19th century, by the end of the 19th century, is that the theory of ordinary differential equation is well developed. Okay, there are only few, I can't say so less, but there are much fewer challenging problems faced with the ordinary differential equations. All right. And so this is about the classifications of PDS. So this is just for you to understand this field. All right. Now we will describe the solutions. Okay. So first of all, use some terminologies in geometry. A domain in an Euclidean space. Euclidean space Rn. Oh, by the way, in this chapter we focus on real value functions. Okay, real value functions. Okay. So that and of course, because you see that independent variables, they are all reals variables. Why? Because in physics, that all the quantities should be real. If you want to measure it, we can't measure complex values. All the instrumental object created or established in the real world can get the real measurement values only. And so if you have a complex value, that would be part of them would be imaginary. So you have imaginary number, right? This is quite, so a complex number has two parts. One is the real part, the other is the imaginary part. Why is it called imaginary? Because it's in your brain. It's you imagine that value. You can't see it in the real world. Yeah, but complex number is very important conceptually. Okay, as you have some experience in circuit theory, right? And also, I think you learned general physics in your freshman year, and I think the professors, sometimes they use complex numbers to solve a problem and to describe some concept, all right? And so there are some beauties of complex numbers or complex variables. That's why in the subject of this semester, we will talk about the complex variables and the functions of complex variables, right? Because they offer beautiful mathematical theories to look at the physical problems, all right? Okay, but anyway, let's, in this chapter, focus on real world. Okay, so a domain in an Euclidean space on N, Xn, is an open and connected subset of Rn. Alright. Okay, there are two concepts called open subset and connected subset. And I should ask you, if any of you, if any of you do not know either concept, please raise your hand. Open and connected. All right. Okay. Thank you. So let me okay. Great. All right. So a subset. All right. So U of an Euclidean space this, or we just say a subset of Rn. And as we see, okay. Do I need to define Rn? Alright, so good of you, right? Good. Alright, so subset of Rn is called open if for each point x in U, right? There exists an open ball, right? Open ball. So B an open ball of center x and radius r. Okay, so an open ball is defined this way, right? The center is x and the radius is r. And so that the distance, you see, this is the distance between, so that in R2, an open ball, so if this is x, and the open ball is just an open disk, right? Here, so if y is here, okay, and so the distance, which is just the square root of y1 minus x1 square plus y2 x2 square. So this is the Euclidean distance. We know that in the plane. Okay. So this is the distance. And so the distance should be less than r here. Should be less than r. Okay. So y in the open ball with the center x. Okay, so y is in the open ball if the Euclidean distance between y and the center x is less than r. Okay, so this here. Right. So we say Ux called open if for each point in U there is an open ball which is contained in U. Okay. All right, and so in R2, I put this one. This region, yeah, and this is U. Then U is an open set, why? Because I select a point here, X here, and I can find an open ball with R here, okay, inside the U. Okay, so U is open. Means that you pick up a point in U, then you can find an open ball with the center x and some radius, and the whole open ball will be inside U. Okay, so that this is the meaning of open. Okay. So this is an open subset of Q, but if you take a score including the boundary, this is V. Then you will see a point on the boundary here. Then any open ball you construct with center X cannot be inside of V. They are part of the open ball will be outside of V. Okay, because that this point is on the boundary, so this V is not an open subset of Q. Okay, so U X an open subset, but this is not one. In three-dimensional space, okay, so if you construct a pyramid here, okay, so including the edges, okay, so this is the pyramid, and so you have okay, so the pyramid and the pyramid is not an open subset of 3. Why? You can select the point, this vertex here, okay? And when you construct an open ball, so this is a three-dimensional ball, okay? Just like a real basketball, okay? Like that. You can see part of the ball, so that say action, maybe action is very small, but this one is not included in the pyramid. Okay, it's not included in it. So that so you see, so basically so the important thing is that for each point, so if a subset U of ion is an open set, if for each point in U, then you can find an open ball with center X, okay, and the whole open ball will be included in U. So that is called open set. Any questions? In one dimension, the open, like an open interval. So AB is an open subset of R. Okay, but A, B, half cross open is not open in R. Why? If in A, at point A, if you construct an open ball actually is just an open interval, right? With the center A, but the radius is R. Okay, so that part of the open ball will be outside of this interval. Okay, so this half closed half open interval is not open in R. But the open interval is an open subset of R. Okay, so that this is about the open set. How about connected set? So a subset is called connected if for any two points x and y in U. Okay, so suppose in R2 and okay, and then you find this is x, okay, and there is another point y here, okay, and this is U. Right, so you select 2 points, and then you can find one line segment to join these 2 points. So you can see one segment, okay. There exists a chain of a line segment which can join x with y. I'm sorry, yes, of finding a chain of line segment which joins x with y. Actually, this definition is called path connected, but in the Euclidean space, the path connected is the same as connected, right? So the general definition of connect to say is very involved. So I use this definition. This is much more easier, and you can see that it's more geometrically. Okay. All right. So now in one-dimensional case, if U is equal to, alright, so in one-dimensional case, in R, so here is 1, 2, okay, so that you have these 2. So U is the union of these 2 intervals. if you pick up a point in the interval here, 1 to 2, so x here, you pick up a point y. Can you find a chain of line segment join? Oh, I have to say, in U, which of course the line segment should be in U, right? Which joins, I'm sorry, is y. Okay. Now, can you find line segment? You can't. Why? Because there are gaps here. The gaps here. So this one is not connected. Right, in R. And so in R1, U is a connected subset if and only if U is an interval. So that's why interval is very important, because an interval in the real line, okay, is the only connected subset you can have. Okay, and the interval can be open interval, closed interval, half open, half closed interval. Yes. Oh, you mean a line?
The edge of the circle is not.
A circle? A circle is
Only the edge. Just can't find finite number.
oh yeah. So interesting. Good question. Yeah, but geometry. A circle is connected, but it cannot be described by past connectedness. Okay. So that's just a trouble. Yeah, the circle should be connected, but how can I set it?
Why is there need to be finite numbers?
Because that would be simple. But if we have even a number of non-segment, then even in a circle, right? It's you can't construct any line segment there. You can't. Okay, so.
By the general definition, the circle is connected. By the general definition, a connected set is like if you're not disconnected.
I know. So that is, I mean, that is open connected, then this is true, yes. That's why. But if it's not open, yes. Okay. So this is stronger. So path connected implies connectedness. But for open set, yeah, they are equivalent to each other. That's true. Okay. Wow. So okay. Maybe I will. Okay. So an open subset. Because fortunately, we need only open connected subset. Great. So that would be much more okay. Yeah. Okay, so open, specific, an open subset is co-connected. If for any points in x1 and u, there is a chain, okay, yeah. There is a chain of a finite number of non-sigma u, which joins x and y. Yeah, so that would be correct. So now I have to, thank you for your comment, that I should put open. Okay, and so any open set? Okay. Because that if it's not open, just like a circle, right? So a circle C such that the circle C is not an open set. Subset of R2. Okay, so obviously, because if you pick up a point on the circle, right, and when you construct an open ball, no matter how small its radius, you can see that another part of the open ball will be outside of the circle. Okay, so a circle, okay, in the plane is not an open subset. Okay. Yeah, but a circle a circle in R2 is connected. Okay, but if okay, so it is but the general definition of connected subset, it's not a very conceptual word. So I don't want to get into that concept. So I rather give you a simple one, right? But this definition is only good for open subset. Okay, only good for open subset. Okay. Actually, I think I will give you a proof when you study complex variables. Okay, in certain chapters, I will write a theorem. Okay, I will write a theorem to prove that because I will give a general definition of connected subset. But for the moment, okay, it's okay now. So that's and a domain. So okay, example, if you make this one, okay, so this opens, so this is the open subset. Okay, so you have an open rectangle and you puncture two holes, right? So you puncture two holes inside the rectangle, you get U here. And this U is an open set. Okay, so U is an open set of R square. And also it is connected. Right, so you can see it by checking that for any 2 points, no matter where they are, you can always find one segment to join them, right? Here. Okay? So geometrically you are able to identify the connectedness of this open set. And also, so this open set is connected. Now, so open subset D of Rn, which, okay, an open and an open and connected subset. D of Rn is called a domain in Rn. Okay. In the origin, say okay, so origin in R is a domain in R plus part of its boundary. Okay, part of its boundary. Okay, so if we include part of the boundary of U, because U is, so now, so U is a domain 2. And if we include part of the boundary, say here, just these two side, and also the boundary of this hole. Okay, so now this one V become 2, so V is a region in 2. Okay, so we will include so we become to a region. Okay. So the concept is that a region is just a domain plus part of the boundary of the domain. Okay. Part of the domain's boundary. Parts, maybe only 1 point. Can be. Maybe anything. Yeah. Yeah, so a domain is also a special kind of region. Yes, but when you talk about domain, it must be open and connected. Okay, and for a region must be connected but may not be open because it includes part of the boundary. Because a point on the boundary, okay, if a region includes part of an empty part of the boundary, then the region becomes to be not open. Not open, okay? Because if you pick up a boundary point and then you construct an open ball with the center at the boundary point, then part of the open ball will be outside of the region. Okay, so that apparently, so if R is not equal to its interior part, then the domain, then this R will not be an open set. Okay. Wow. Alright, so now a solution of a PDE in some region of the space of the independent variables. If there are two independent variables, then the space will be two-dimensional. So that will be a plane, right? But if there are three independent variables, then we're considering the three-dimensional Euclidean space. Okay. All right. So a solution in some region of the space of independent variables is a function. Okay, it's a function that has all the partial derivatives appearing in the PDE in some domain D containing R. Okay. And so if we look at PDE and we find that a solution in some region R, okay, then this solution must be a function, okay, and that has all the partial derivatives, okay, appearing in the PDE, okay. For example, in the second order linear PDEs, that they are second order partial derivatives and the first order partial derivatives, and we ask that the solution has all these second order partial derivatives and the first order partial derivatives in some domain D containing R. Okay, so usually we ask for that. Usually, so maybe just like Okay, so this is R. Okay, but we may ask for that the solution corresponding to a function which is defined on a bigger subset D, which is the domain. And R is a region. Okay, so the domain D containing R. Okay, and because when we define derivatives, we always define in an open subset. Okay, so if you remember when you study the partial derivatives in your calculus, right, you can see that they are usually the defining domain will be actually a domain. Okay, I'm sorry that they use the same word, right? That here the domain is just open connected set. But basically it is an open set. Okay, so that so we want that the all partial derivatives appearing in some domain D. Okay, and of course satisfy the PD everywhere. Okay, in the region R. Okay, and but often I have to make a remark. Often the function, okay, for the solution is only required to be continuous on the boundary, okay, of the region R. And to have those derivatives in the interior of R. And to satisfy the PD in the interior of R. Okay. As we know, the region is a domain, including part of the boundary of the domains. Okay, but so the interior of R actually is just the domain. Okay, and there's a domain there. Okay. So sometimes we actually, so that this situation is here. Okay. Right. So this is the domain, and the region will be the domain including some part of the boundaries here. Okay, so this is the R here. Okay, and we want the solution is a function which is continuous, right, on the boundary. Okay, and then has derivatives inside the region here. Actually, this domain. All the derivatives, second order derivative, first order derivatives for all the points inside of the region. Okay, so the interior of the region, and this derivative would satisfy the PDE in the interior points of the R. Okay, so that the interior is the domain which comprises R. Okay? Okay, so that when we try to find solution of a PDE, and actually we will find a function defined on a region, okay, of the space of the independent variables. Okay, so the region there. Okay. Another point, in general, the totality of solutions of a PDE is very huge. For example, the following functions, right, of two independent variables, okay, E equal to E of e to x and the cosine y, E is equal to the sine x and the hypercosine y, E equal to the natural logarithm of, okay. And you can see this function, the defined domain, so that the region is defined. Here is R square, this is R square, so the whole plane, and for this one, this is also the R square. But how about this? This is the R square, but remove the origin, right? Because if x equals 0, y equals 0, you have a natural logarithm of 0, which is undefined. Okay, so the region, the defining region, for this one, so we have 1, 2, 3, 4, these 4 functions, you can see they have the different defining region there. Okay. And these functions are solutions, okay, of the two-dimensional Laplace equation. So they are all solutions of these two-dimensional Laplace equations. You can justify them. So for this one, you know this is 2x, okay, and this is minus 2y, okay. Now, so uxx is equal to 2. Okay, and uxy equal to 0. And this is uyx, and uyy equal to minus 2. Okay, so that's uxx plus uyy is 2 minus 2 is 0. Okay. Right, so you see this is actually by checking, right? So this function is a solution of the two-dimensional Laplace equation. For this one, you can say it's minus, okay, this is first partial derivatives, and then uxx is again, okay, and y, but uyy, so this is minus cosine y here. And then, so you add them together, which is 0 for all xy again. So that, and for this one, you take the cosine and x y here, and your y, then you have the minus sin x and sin hy, okay, and the uxx, you give you minus sine and cosine hy and the uyy, okay, so this is minus sin x cosine oh, I'm sorry, here. So this is, okay. Alright, so ux plus uyy is equal to minus sine cosine hy plus sine cosine hy. So this is equal to 0 again. And for this one, ux is equal to x squared plus y squared, and 2x, and y is equal to, okay, and uxx so this is equal to minus 2x and 2x here, and then y square 2 minus 2y. Okay, so x, what is that? So this is the 2y square minus 2x square plus 2x square minus 2y square. Okay, and I cancel them, so this is 0 again. Okay. So you check that these four functions really satisfy the two-dimensional Laplace equations. Okay, so and you can see that they are quite different functions, right? They are quite different by nature, and but they all satisfy the same partial differential equations. Right. So this is illustrates the complication to find a solution. Okay. Especially to find a general solution. Okay. The general solution. Okay, so to find general solution is quite a huge problem, but in physics, right, from the problems usually has unique solutions. So the unique solution of a PDE corresponding to a given physical problem will be obtained by the use of additional conditions arising from the problem. Okay. Because from physics we know that for dynamic systems, we use PDE to describe dynamic systems. And there are some conditions for the physical systems. So that's why there should be one and only one solutions, because this exists in the real world, in the physical world. So our goal will become to find such a unique solution. Okay, when additional conditions can be obtained from the related problems. Okay, and then very interestingly, to find such a unique solution becomes to be much more easier than to find a general solution. Okay, a general solution. So our targets in this chapter are to find unique solutions. Okay? Yeah, to simplify the problem. Otherwise, we have to discuss more tools before we can study the general solution of a PDE. Okay? It's not like the way we study the ordinary differential equation last semester. Okay? Because there are, for ODE, we usually say we can find the general solutions. Right? And then with initial condition or something, special condition, we can find unique solutions for some of them. Okay. All right, and so for instance, so this may be the condition, right, that solution U assumes given values, right, on the boundary on the boundary of the region. So we call boundary conditions. Alright? So we ask that the solution should assume some given values, okay, on the boundary of the defining region. So they are called boundary conditions. Or when term T is one of the variables, for example, in the heat equation or wave equations, the U or the first order partial derivatives or both. Okay, so U or the first order partial derivatives may be prescribed at time equal to 0. So they are called initial conditions. Okay? Right, so we will use boundary conditions or and initial condition, right, together with a PDE to find a unique solution. Okay. Okay. And so now I state a general thing in this section, which appear in the textbook. We call the fundamental theorem of superposition. Now, so if U1 and U2 are solutions of a homogeneous linear PDEs in some region R, then with any constants C1 and C2, the mean function U equal to C1 plus C2U2, this new function is also a solution of that PDE in the region R. in the region over here. Okay, so I just state the theorem, and on the coming Thursday I will give a proof, a very short proof, because the proof of this theorem is very simple. But you need to write down a general formula for a homogeneous linear PDE with any order. Okay, because I just give you a general form of second order linear ODE, right? But how do you write down a general n-order linear ODE PDE? Okay, if the order is n, just arbitrary n. So how can you find that? All right. So that once you can write down such a homogeneous linear PDE, then you can prove this thing immediately. Okay. Okay, so I stop here. I'm sorry I didn't give you a breakdown. Okay. Okay.